Hello there, and welcome to the Deep Somna. I'm so glad you found your way here, because tonight we're turning our gaze upward to follow the silent descent of cosmic travelers across the dark sky. Close your eyes now if you haven't already. Let the weight of your body sink a little deeper into whatever surface holds you. The day is done. The noise has faded. And here, in this quiet pocket of time, you don't need to do anything at all, except listen and let your mind wander softly through the dark. Tonight, we're going to think about something simple. Something that happens above your head every single day, whether you notice it or not. We're going to think about meteors, those brief streaks of light that cross the night sky. The ones we sometimes call shooting stars, even though they're not stars at all. You've probably seen one before. Maybe you were lying on your back in a field, or standing on a beach, or sitting in a backyard chair on a warm summer night. And then, without warning, a line of light appeared. It traveled across the darkness for just a second, maybe two, and then it was gone. And you might have smiled, you might have made a wish, or you might have simply watched in quiet amazement, wondering what it was you'd just seen. What you saw was a meteor, a tiny piece of the universe burning up as it fell through Earth's atmosphere. Most of them are no bigger than a grain of sand. Some are the size of a pebble. A few, very rarely, are much larger. But all of them share the same fate. They fall. They burn. They light the sky for a heartbeat, and then they vanish. And yet, in that brief moment, they tell us something profound. They remind us that the sky is not empty, that space is not a void, that the universe is full of motion, full of matter, full of silent travelers moving through the dark. You don't have to understand all the details tonight. You don't have to memorize the numbers or the names. All you have to do is let the images wash over you. Let the ideas settle gently in your mind like dust falling through still air. And if you drift away before we're finished, that's perfectly fine. That's exactly what this is for. So take a slow breath in, let it out, and let's begin. Imagine, for a moment, that you're floating high above the Earth, not in a spacecraft, not in any kind of vessel at all. Just you, suspended in the quiet blackness of space, looking down at the planet below. From here, the Earth looks impossibly beautiful. Blue and white and brown, wrapped in swirling clouds, glowing softly in the light of the sun. But you're not alone up here. All around you, invisible to your eyes, there are tiny fragments of rock and metal. Some are drifting slowly. Others are moving at incredible speeds, thousands of miles per hour, racing along invisible paths that curve and loop through the solar system. These are meteoroids, the technical name for the objects that will one day become meteors. They come from many places. Some were born in the asteroid belt, that vast ring of rocky debris that orbits the sun between Mars and Jupiter. Billions of years ago, when the planets were still forming, this material never quite came together into a world of its own. Instead, it remained scattered, a population of wanderers. Occasionally, two asteroids collide. The impact sends fragments flying in all directions, and some of those fragments, over time, find their way toward the inner solar system, toward Earth. Others come from comets. Comets are different from asteroids. They're not solid rock. They're more like dirty snowballs, mixtures of ice and dust, and frozen gases. Leftovers from the outer reaches of the solar system where it's cold and dark and still. When a comet swings close to the sun, the heat causes its surface to vaporize. Jets of gas and dust stream away, forming the comet's glowing tail. But the tail doesn't disappear. It spreads out along the comet's orbit, creating a river of particles that hangs in space long after the comet itself has passed. And Earth, in its endless journey around the sun, crosses through these rivers. Year after year, orbit after orbit, our planet sweeps through the debris trails left by comets that passed this way centuries, even millennia ago. When that happens, we see meteor showers, dozens, sometimes hundreds of tiny particles entering the atmosphere in a single night, all of them coming from the same direction in the sky, all of them remnants of the same ancient comet. But you don't need to wait for a meteor shower to see a meteor. Every single day, even in broad daylight, meteoroids are falling toward Earth. Scientists estimate that more than 100 tons of space material enters our atmosphere every 24 hours. Most of it is dust. Invisible, silent, too small to see. But it's there, drifting down like an endless, gentle rain from the cosmos. Let that image sit with you for a moment. 100 tons, every day, falling from space, most of it so fine that it simply floats down through the air and settles on rooftops, on trees, on the surface of the ocean. You've probably breathed in a particle or two without ever knowing it. You've certainly walked on ground that contains countless microscopic fragments from asteroids and comets. The boundary between Earth and space is not as clear as we sometimes imagine. The universe is touching us constantly, quietly, in ways we almost never notice. Now let's follow one of these particles. Let's imagine a single grain of dust, no bigger than the period at the end of this sentence, drifting through space. It's been traveling for a very long time. Maybe it was once part of a comet that formed 4.5 billion years ago, back when the solar system was young and the planets were still gathering themselves together. For billions of years, this tiny speck has been moving through the void, silent and invisible, untouched by anything except the faint pressure of sunlight and the distant pull of gravity. And then, one day, its path intersects with Earth. It doesn't know this, of course. It has no awareness, no destination. It's just following the laws of motion and gravity, the same laws that govern everything in the universe, from the smallest atom to the largest galaxy. But now, for the first time in its long existence, it's about to meet the atmosphere. The atmosphere is a thin shell of gas that surrounds our planet. From space, it looks delicate, almost fragile, like a faint blue haze clinging to the Earth's surface. But appearances can be deceiving. The atmosphere is thick enough, dense enough, and fast-moving enough to protect us from almost everything the universe throws at us. And when our tiny dust grain hits it, moving at perhaps 30 or 40,000 miles per hour, something extraordinary happens. The air in front of the particle can't get out of the way fast enough. It compresses, and when air compresses that quickly, it heats up, not just a little, a lot. The temperature around the particle climbs rapidly, reaching thousands of degrees in a fraction of a second. The heat is so intense that the air itself begins to glow. Nitrogen and oxygen molecules, stripped of their electrons, emit light. The particle, too, starts to vaporize, its surface peeling away layer by layer, turning from solid matter into glowing plasma. And that's what we see from the ground, that brief streak of light in the sky. That's not the rock itself glowing. It's the air around it, transformed by speed and pressure and heat into a shining trail. The meteor, as we call it now that it's entered the atmosphere, exists for only a second or two. By the time you've noticed it, it's often already gone. The particle that traveled through space for millions or billions of years has been consumed in a flash, transformed entirely into light and heat, and a tiny puff of vapor that disperses into the upper atmosphere. Most meteors burn up completely. They never reach the ground. They're too small, too fragile. The atmosphere does its job, turning them into brief sparks and nothing more. But every now and then, something larger survives. A fragment big enough to withstand the heat, or moving at just the right angle, or made of just the right material. When that happens, when a meteoroid makes it all the way through the atmosphere and lands on Earth's surface, we call it a meteorite. And meteorites are treasures. They're pieces of other worlds, delivered to us by gravity and chance. People have been finding meteorites for thousands of years, long before anyone understood what they were. Ancient cultures saw them fall from the sky and considered them sacred, gifts from the gods. Some meteorites were shaped into tools or weapons. Others were placed in temples or buried with the dead. Even today, when we understand their origin, there's something almost magical about holding a meteorite in your hand. You're holding an object that's older than any rock on Earth. Older in many cases than the planet itself. You're holding a fragment of the early solar system, unchanged and unweathered, a direct connection to a time when the sun was young and the planets were still forming. Some meteorites are made mostly of stone. These are the most common type. They're rocky, grayish, often speckled with tiny flecks of metal. If you didn't know what you were looking at, you might walk right past one. It wouldn't look particularly special. But if you picked it up, you might notice that it's heavier than you'd expect. And if you looked closely, you might see a thin, dark coating on the outside, called a fusion crust. That's the melted surface, the part that was flash heated during its descent through the atmosphere. It cooled almost instantly when the meteorite landed, freezing the moment of entry into a smooth, glassy shell. Other meteorites are made mostly of metal, iron and nickel, forged in the cores of ancient asteroids. These are rarer, but they're unmistakable. They're heavy, dense, magnetic. When you cut one open and polish it, you often see beautiful crystalline patterns, intricate geometric structures that can't form anywhere on Earth. These patterns, called Widman-Stettin patterns, only appear in metal that cooled incredibly slowly over millions of years in the heart of an asteroid. It's like a fingerprint, proof of the meteorite's extraterrestrial origin. And then there are the rarest meteorites of all, the ones that come not from asteroids or comets, but from other planets, from the moon, from Mars. This sounds impossible, but it's true. When a large asteroid or comet strikes the surface of a planet, The impact is so violent that it can launch rocks into space. Most of that material falls back down, of course, but some of it, ejected at just the right speed and angle, escapes the planet's gravity entirely. It becomes a new meteoroid, wandering the solar system, carrying with it a piece of the world it left behind. Scientists have identified dozens of meteorites that originated on Mars. They know this because the chemistry of these rocks matches what we've measured on the Martian surface. Some even contain tiny bubbles of trapped gas, and when researchers analyze that gas, they find it's identical to Mars's atmosphere. These meteorites are priceless. They're the only samples of Mars we have on Earth, aside from the tiny amounts returned by robotic missions. And they got here entirely by accident, launched by ancient impacts, traveling through space for millions of years, and finally falling to Earth where someone, by chance, found them lying in a desert or frozen in Antarctic ice. It's easy to let your mind wander when you think about this. To imagine a rock resting on the Martian surface 3 million years ago, watching the sun set over rust-colored dunes, and then, suddenly, impact. A flash of light, unimaginable violence, and this rock, along with countless others, thrown upward faster and faster, until it breaks free from Mars entirely and begins a new journey through the void. For millions of years, it drifts, silent, alone, no destination, no purpose, just movement, governed by gravity and momentum. And then, against all odds, it crosses paths with Earth. It falls through our sky, glowing bright orange as it descends. It crashes into a field, or a desert, or an ice sheet, and there it waits. Days, years, centuries, until someone stumbles across it and picks it up and wonders, for just a moment, what this strange, heavy rock might be. That meteorite is a messenger, a piece of another world, carrying the story of a violent past, now resting quietly in someone's hand. You can let your breathing slow now. Let your body relax a little more. We're going to keep moving through this story, but there's no rush, no urgency. The meteors will keep falling whether we're awake or asleep. The universe will keep turning, and you can simply rest here, listening, letting the words flow over you like a gentle current. Let's think for a moment about what happens when you actually see a meteor. You're outside on a clear night. Maybe you've driven somewhere away from the city lights, somewhere the sky is truly dark. You lie back on a blanket, or on the hood of a car, or on the cool grass. Above you, the stars are everywhere. Thousands of them, maybe more than you've ever seen at once. The Milky Way, if you're lucky, arcs overhead like a river of light, and you wait. At first, nothing happens. The sky is still. The stars don't move, or at least they don't seem to. They're so far away that their motion is imperceptible to your eyes. But you keep watching. Your eyes adjust to the darkness. You start to notice things you didn't see before. The faint glow of a distant galaxy. The steady, patient light of a planet. And then, without warning, it happens. A streak of light. Thin, bright, silent. It appears in the corner of your vision and races across a small section of the sky before vanishing. The whole thing lasts maybe 2 seconds, maybe less. and then it's gone, as if it never existed, but you saw it. You were looking in the right direction at exactly the right moments. And for those 2 seconds, you were connected to something immense. A particle from space, a fragment of the cosmos, burning up in real time, right there in front of you. There's something deeply satisfying about seeing a meteor. It's not dramatic in the way a thunderstorm is dramatic. There's no sound, no rumble, no crash. It's quiet, fleeting, but it's real. You didn't imagine it. Something actually fell from space and lit up the sky just for you. And even though you know, intellectually, that it was just a tiny piece of rock or ice, smaller than a marble, there's still a part of you that feels wonder, that feels grateful to have witnessed it. This is what makes meteor showers so special. During a meteor shower, Earth is passing through a particularly dense stream of debris, usually left behind by a comet. The result is that you see many more meteors than usual. Instead of waiting an hour to see one, you might see several in just a few minutes. And because they're all coming from the same source, they all appear to radiate from the same point in the sky, called the radiant. The most famous meteor showers have names that come from the constellations where their radiants are located. The Perseids, for example, appear to come from the constellation Perseus. They occur every August, when Earth crosses the debris trail of a comet called Swift-Tuttle. On a good year, in a dark location, you can see up to 100 Perseid meteors in a single hour. Some of them are faint, quick flashes. Others are bright fireballs that leave glowing trails across the sky. The Geminids, which occur in December, are another reliable shower. They're unusual because they come from an object called 3200 Phaethon, which is classified as an asteroid, not a comet. But Phaethon behaves a bit like a comet when it gets close to the sun, shedding dust and small fragments that eventually become the Geminid meteors we see each December. The Geminids are known for producing bright meteors, often yellow or white, and they're one of the few major showers that are best viewed before midnight. There's something peaceful about lying under the stars during a meteor shower. You're not doing anything, really. Just watching, waiting, letting your thoughts wander, and every few minutes, the sky rewards you with a brief flash of light, a reminder that you're part of something much larger than yourself, that the Earth is a small planet orbiting an average star in an unremarkable part of an ordinary galaxy. And yet, here you are, alive and aware, watching ancient dust burn up in the atmosphere. It's humbling and beautiful at the same time. Sometimes, very rarely, a meteor is large enough and bright enough to be called a fireball. Fireballs are meteors that outshine the planets. Some are even brighter than the full moon. Up in the full moon, they can cast shadows on the ground. They can light up clouds from below, turning the night sky into a brief, eerie daylight. And sometimes, when a fireball breaks apart or explodes in the atmosphere, you can hear it. A distant rumble or boom, arriving seconds or even minutes after the flash of light, because sound travels so much slower than light. These events are rare, but they happen. And when they do, they're often captured on camera. In recent years, with the spread of security cameras and dashboard cameras, many fireballs have been recorded by chance. People share the videos online, and scientists study them, trying to calculate the meteor's trajectory and figure out where fragments might have landed. Sometimes those fragments are found, and when they are, they're incredibly valuable, both scientifically and personally. There's something extraordinary about holding a piece of rock that just fell from the sky, that was in space hours or days ago, and is now resting in your hands. Let your mind rest on that image for a moment. A fireball, bright enough to light up the night. A streak of brilliant white or green or orange, tearing across the sky, and then the sound, delayed, rolling like thunder across the landscape. It's one of those experiences that stays with you, that reminds you how dynamic the universe really is, how much is happening all the time even when we're not looking. But most of the time, meteors are quiet, gentle. They come and go without fanfare. And that's part of their beauty. They don't shout or flash or make noise. They simply appear, briefly, and then fade away, like a whisper from the cosmos. A small reminder that we're not separate from space. We're part of it. We're made of the same matter. We're subject to the same forces. And every now and then, a tiny piece of that vast universe falls down through our sky and reminds us of the connection. Take another slow breath if you'd like. Feel your shoulders drop, your jaw soften. There's nothing you need to hold on to right now. No tension you need to carry. We're going to keep drifting through this story together, moving gently from one thought to the next, like leaves floating down a quiet stream. Let's think about time for a moment. Not the time on your clock, or the time you need to wake up in the morning, but deep time, cosmic time, the kind of time that's hard for our minds to truly grasp. When you see a meteor flash across the sky, you're witnessing the end of a journey that began unimaginably long ago. That tiny fragment might be 4.5 billion years old. Older than the mountains, older than the oceans, older than the Earth itself. 4.5 billion years. Let that number sit with you gently. Don't try to understand it fully. No one really can. But imagine, just for a moment, that you could watch that entire span of time unfold like a movie. You'd see the solar system forming. You'd see a vast cloud of gas and dust, light years across, slowly collapsing under its own gravity. At the center, pressure and temperature rise until nuclear fusion ignites. The sun is born. A new star, one among billions in the galaxy. But the sun doesn't form alone. All around it, in a flat disk of swirling material, small particles begin to stick together. Dust grains collide and cling. Over time, they build up into pebbles, then boulders. Gravity pulls these growing objects together. Some become large enough to be called planetesimals, the building blocks of planets, and slowly, over millions of years, the planetesimals themselves collide and merge, forming larger and larger bodies. The inner solar system becomes rocky and hot. The outer solar system, cold and icy. Our meteor, our tiny fragment, might have formed during this time. It might have been part of a larger body that never quite became a planet. Or it might have been ejected from a collision between two growing planetesimals. Whatever its origin, it ended up adrift, orbiting the sun along with countless other fragments, waiting in a sense, though of course it has no awareness, no anticipation. It's just matter, following the laws of physics, moving through space. And for billions of years, nothing much happens to it. It orbits. Sometimes its path brings it close to other objects. Sometimes it passes through regions where ice sublimates into gas, or where radiation from the sun alters its surface chemistry. But mostly it just drifts, silent, unchanging, a witness to the slow evolution of the solar system. Though it records nothing and remembers nothing, the planets settle into stable orbits. Earth forms and cools. Oceans appear. Life emerges, first as simple cells, then as more complex organisms. Continents drift. Ice ages come and go. Species evolve and go extinct. Mountains rise and erode away. And through all of this, through every moment of Earth's history, our fragment is out there, orbiting the sun, untouched by any of it. Until finally, one day, gravity nudges its orbit slightly. Maybe a close pass by Jupiter. Maybe a distant interaction with another asteroid. The change is tiny, but it's enough. Over time, the fragment's path gradually shifts. And one day, 4.5 billion years after its formation, its trajectory intersects with Earth's orbit. And in the span of a few seconds, the entire journey ends. The fragment enters the atmosphere, heats up, glows, and vanishes. Transformed from solid matter into light and heat and dispersed atoms. When you think about it this way, every meteor is extraordinary. It doesn't matter how small it is. It doesn't matter if anyone sees it. Each one represents an inconceivable journey through time. Each one is a piece of the solar system's history, arriving at our planet by chance. And when it burns up, it's not really being destroyed. Not in a fundamental sense. The atoms that made up that fragment don't disappear. They're just rearranged. Some of them might end up in the air you breathe. Some might settle into the soil. And billions of years from now, they might be part of something else entirely. This is one of the quiet truths that meteors teach us. Nothing in the universe is permanent. Everything changes. Everything transforms. Dust becomes rocks. Rocks become planets. Planets are struck by asteroids and fragments scatter. Those fragments orbit for eons, then fall through atmospheres and become meteors. And the atoms from those meteors eventually become part of new structures, new worlds, new life. It's a cycle that's been happening since the universe began, and it will continue long after we're gone. You don't need to hold on to any of this tightly. You can let these thoughts drift through your mind the way meteors drift through space. Gently, without force. There's no test at the end. No need to remember every detail. What matters is the feeling, the quiet sense of connection, the reminder that we're all made of ancient material. Stardust, as Carl Sagan famously said, and it's true. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in the hearts of stars that lived and died long before the sun ever existed. And some of it, a small amount, arrived here on Earth carried by meteorites. Scientists have found meteorites that contain amino acids. These are the building blocks of proteins, the molecules that life depends on. The amino acids in these meteorites formed in space, in the cold, dark regions between stars, or in the icy bodies at the edge of the solar system. They're not life, they're not even close, but they're the raw materials that life needs. And when meteorites containing these molecules fell to Earth billions of years ago, they might have helped jumpstart the chemical processes that eventually led to the first living cells. This idea is called panspermia, or at least a version of it. The notion that some of the ingredients for life came from space, delivered by comets and meteorites during Earth's early history. We don't know if this is true. It's one possibility among many. But it's a beautiful thought. That life on Earth, in some small way, might owe its existence to fragments falling from the sky, that were not separate from the cosmos, but deeply connected to it, shaped by it, made possible by it. And even if panspermia isn't the full answer, we know for certain that meteorites have influenced Earth's history in profound ways. They've delivered water. They've delivered carbon and other essential elements. And on at least one occasion, a very large meteorite struck the Earth with enough force to change the course of life on the planet entirely. You might have heard of this event. It happened 66 million years ago, at the end of the Cretaceous period. A massive object about 10 kilometers wide slammed into what is now the Yucatan Peninsula in Mexico. The impact created a crater over 150 kilometers in diameter. The energy released was equivalent to billions of nuclear bombs going off at once. The immediate effects were catastrophic. Tsunamis swept across the oceans. Wildfires raged across entire continents. But the long-term effects were even more significant. The impact threw enormous amounts of dust and debris into the atmosphere. So much material that it blocked out sunlight for months, maybe years. Temperatures dropped. Photosynthesis slowed or stopped. Plants died. Carnivores had nothing to eat. And within a relatively short period of time, about 75% of all species on Earth went extinct, including, most famously, the non-avian dinosaurs. The dinosaurs had ruled the Earth for over 160 million years. They'd survived ice ages, volcanic eruptions, shifting continents. But they couldn't survive the aftermath of this impact. And in their absence, a new group of animals rose to prominence. Mammals, which had existed for millions of years as small, mostly nocturnal creatures, began to diversify and spread. Over time, they evolved into countless forms, and eventually, tens of millions of years later, one branch of the mammal family tree led to primates, to apes, to humans. So in a very real sense, you exist because of a meteor. If that impact hadn't happened, if that particular rock hadn't been on that particular trajectory, the dinosaurs might still be here. And mammals might still be small, scurrying creatures hiding in burrows and under logs. There would be no humans, no cities, no art or music or science. The entire course of Earth's history would have been different. It's a humbling thought. Our existence, in this form, at this time, is the result of countless accidents and contingencies. One of them was a meteor strike that happened 66 million years ago, an object that had been drifting through space for billions of years, completely indifferent to Earth, to life, to anything. And then one day, it arrived, and everything changed. But you don't need to dwell on the violence of it, the destruction. What's more interesting, perhaps, is the reminder that change is constant, that the universe is always in motion, that impacts happen, that species rise and fall, that nothing stays the same forever. And that's okay. It's not frightening. It's just the way things are, the way things have always been. Let your mind rest on something quieter now. Imagine a different scene, not an impact, not destruction, just a peaceful moment somewhere in the desert. It's early morning. The sun is just beginning to rise, painting the sky in shades of pink and orange. The air is cool and still, and there, lying on the sand, half buried, is a meteorite. It fell here centuries ago, maybe longer. There were no witnesses. No one saw the flash of light in the sky. No one heard the sonic boom as it descended. It simply landed, kicked up a small spray of dust, and then settled. And there it's been ever since, waiting. The wind has buried it slightly. The surface has darkened from exposure to the sun. But it's still a visitor from space, still carrying the record of its ancient origin. And then, one day, someone finds it. Maybe a geologist out doing field work, maybe a hiker who stopped to rest and happened to notice something unusual sticking out of the sand. They pick it up. It's heavier than they expected, denser. They turn it over in their hands, noticing the fusion crust, the metallic flecks, the unusual texture, and slowly, it dawns on them what they're holding. This isn't an ordinary rock. This is a meteorite, a piece of space, a fragment of the solar system's history, now resting in their palm. In that moment, there's a kind of quiet awe, a sense of connection to something vast and ancient. They're holding an object that's older than almost anything on Earth. An object that's traveled farther than they ever will. An object that formed in conditions they can barely imagine. And now it's here, on Earth, in their hands. Delivered by gravity and time and pure chance. This is what meteorites do. They bridge the gap between here and there, between now and then. They make the abstract concrete. When you read about the solar system forming billions of years ago, it's hard to really feel it. It's just words, numbers. But when you hold a meteorite, suddenly it's real, tangible. You're touching that history. You're connected to it in a direct, physical way. Some meteorites are displayed in museums, behind glass, carefully labeled, with placards explaining where they came from and when they fell. But others are held by private collectors, or kept by the people who found them. And a few, a very few, are still out there, uncollected, lying in deserts or fields or forests or ice, waiting for someone to stumble across them, waiting to tell their story. Antarctica is actually one of the best places on Earth to find meteorites. This might seem counterintuitive. It's cold, remote, inhospitable, but those are exactly the reasons it works so well. Meteorites that fall on the ice are preserved almost perfectly. There's no weathering, no erosion, and the dark rocks stand out clearly against the white ice. Even better, the movement of ice sheets tends to concentrate meteorites in certain areas. Glaciers flow slowly toward the coast, but when they encounter mountains or other obstacles, the ice grinds to a halt. And over thousands of years, meteorites that fell in different places, at different times, all get deposited in these stranding zones. Scientists travel to Antarctica regularly to collect meteorites. They work in teams, moving slowly across the ice on foot or by snowmobile, scanning the surface for any dark objects. When they find one, they photograph it, record its location, and carefully place it in a sterile bag. Later, back at a research station, the meteorites are cataloged and shipped to laboratories where they're studied in detail. Tens of thousands of meteorites have been recovered from Antarctica. Each one is unique. Each one has its own story. And together, they've taught us an incredible amount about the early solar system, about how planets form, about the processes that occur in asteroid interiors, about the chemistry of comets, about the age and composition of the sun. You can let your breathing slow even more now. Let your thoughts drift. We're going to keep moving through this story, but there's no hurry. The meteorites will keep falling. The scientists will keep studying them. The universe will keep turning. And you can simply rest here, listening, letting the words wash over you like a tide. Think about the sound of a meteor. Or rather, the lack of sound. When you see a meteor streak across the sky, it's completely silent. There's no whoosh, no crackle, no roar. Just light. The meteor is too high up, too far away for any sound to reach you. It's moving through the thin upper atmosphere, 50 or 60 miles above your head. Even if it did make noise, which it doesn't, you'd never hear it. But sometimes, with very large meteors, with fireballs, you can hear something. Not at the moment you see the light. That's still silent. But seconds later, sometimes even a minute or two later, a sound arrives. A deep rumble, a crack, a series of booms. This is the sonic boom created by the meteor's passage through the atmosphere. Like a jet plane breaking the sound barrier, but much larger, much more powerful. The sound has traveled all the way from the upper atmosphere down to the ground, and by the time it reaches your ears, it's softened and spread out. But it's still there, a ghostly echo of an event that's already over. There's something eerie about this delay. You see the light, the flash, the brilliant streak, and then nothing, silence, and you start to think maybe that's all there is. But then, just when you've almost forgotten, the sound arrives, rolling across the landscape like distant thunder. It reminds you that what you saw wasn't just a visual phenomenon. It was a physical event, an object moving through air, compressing it, heating it, creating pressure waves that ripple outward. In 2013, a meteor exploded over Chelyabinsk, Russia. It was a superbolide, one of the brightest meteors recorded in modern times. The object was about 20 meters across, and it entered the atmosphere at a shallow angle, moving at about 60,000 kilometers per hour. As it descended, the pressure and heat became too much for the meteorite to withstand, and at an altitude of about 30 kilometers, it exploded. The flash of light was bright enough to be seen for hundreds of kilometers. People captured it on dashboard cameras and security cameras. It looked like a second sun rising in the sky. And then, about 90 seconds later, the shockwave arrived. Windows shattered across the city. Buildings shook. Over 1,000 people were injured, mostly from flying glass. But remarkably, no one was killed. The Chelyabinsk meteor was a wake-up call. It reminded people that meteor impacts aren't just ancient history. They're not something that only happens in movies. They're real. They're ongoing. And while most meteors are harmless, every now and then, something larger arrives. Something that can cause real damage. but you don't need to be afraid. The odds of being harmed by a meteor are vanishingly small, far smaller than the odds of being struck by lightning, far smaller than countless everyday risks we don't even think about. And even the Chelyabinsk event, as dramatic as it was relatively minor. The meteor exploded high in the atmosphere. Most of its energy was released up there, not at ground level. If it had been just slightly different, larger, or on a steeper trajectory, the outcome could have been much worse. Still, it's worth thinking about. Not with fear, but with a kind of sober awareness. The universe is not static, space is not empty. And Earth, as it orbits the sun, is constantly moving through a field of debris. Most of it is tiny, harmless, but some of it is larger. And occasionally, very occasionally, something big enough to matter arrives. It's part of the natural rhythm of the solar system. It's been happening for billions of years, and it will continue to happen for billions more. But that's a thought for another time. For now, just let it drift away. Let your body sink deeper into rest. Let your mind grow softer, quieter, like the sky just before dawn. We're going to keep moving through this story, through the science and the history and the quiet wonder of meteors, but there's no need to hold on to any of it tightly. Just let it flow. Your breathing has probably slowed by now. That's good. That's exactly what should happen. Your body knows how to rest. It knows how to let go. All you have to do is allow it. And while you're drifting here, we'll keep thinking about meteors, about these silent travelers, about what they mean, and where they come from and why they matter. There's a question that people sometimes ask. A simple question, but one that opens up into something profound. Why do meteors glow different colors? You've probably noticed this if you've seen more than one. Some meteors are white or yellow. Others are green or blue. Occasionally you'll see one that's orange or red. These colors aren't random. They're telling you something about what the meteor is made of. When a meteor heats up in the atmosphere, the atoms in it become excited. They gain energy. And when they release that energy, they emit light at specific wavelengths. Different elements emit different colors. Sodium, for example, glows yellow. That's the same reason sodium street lamps are yellow. Magnesium burns white. Calcium produces a violet hue, though it's often faint and hard to see. Iron and nickel, which are common in many meteorites, produce yellows and greens. The atmosphere itself contributes color too. Nitrogen and oxygen, the main components of air, emit blues and greens when they're ionized. So the color you see in a meteor is a combination of the meteor's composition and the atmospheric gases it's interacting with. It's like a chemical signature, a brief flash of information written in light. And there's something poetic about that, the fact that you can look at a meteor and, just from its color, know something about what it's made of. You can see the iron, the magnesium, the sodium, elements that formed in stars billions of years ago, now glowing briefly as they pass through our sky. It's a reminder that everything in the universe is connected, that the atoms in that meteor are the same kinds of atoms that are in your body, in the air, in the ground beneath you, Let that thought settle gently. You don't need to analyze it. Just let it be there, like a warm blanket. The idea that you're made of the same stuff as meteors, as stars, as galaxies. It's true in the most literal sense. Every atom of carbon, oxygen, nitrogen, iron, everything except hydrogen and helium was created inside a star. And when that star died, whether in a supernova explosion or a slower, gentler ejection of its outer layers, those atoms were released into space. They drifted. They mixed with other material. And eventually they became part of new clouds of gas and dust. New solar systems, new planets, new life. So when you see a meteor, you're not just watching a rock burn up. You're watching a piece of the universe returning to the universe. You're watching matter transform, energy being released. A cycle that's been happening since the beginning of time. And you're part of that cycle too, not separate from it, not above it or outside it. Part of it, completely and fundamentally. This is one of the things science does so beautifully. It connects us to the cosmos. It shows us that we're not isolated, we're not alone. We're woven into the fabric of reality in ways that are both humbling and uplifting. And meteors, in their quiet way, are one of the clearest examples of this. They're fragments of space that touch our world, that become part of our world, that remind us every time they appear that the boundaries we imagine between Earth and space are artificial, permeable, always being crossed. Now think about the people who study meteors. The scientists who dedicate their lives to understanding these objects. They're called meteoriticists, and they work in laboratories all over the world. They use microscopes and spectrometers and mass spectrometers to analyze meteorites in incredible detail. They measure isotope ratios to determine the age of the material. They study crystal structures to understand the thermal history. They look for organic molecules, for water, for clues about the early solar system. And what they've discovered is astonishing. Meteorites contain some of the oldest solid material in the solar system. Tiny grains, called Preseler grains, that formed before the sun even existed. These grains condensed in the atmospheres of dying stars, were blown out into space, and eventually became incorporated into the cloud of gas and dust that collapsed to form our solar system. They're literally older than the sun, older than the planets, older than anything else we can hold in our hands. When scientists find these Preseler grains in meteorites, they can study them to learn about the stars they came from. Different stars produce different isotopic signatures. So by analyzing the isotopes in a Preseler grain, researchers can figure out what kind of star it formed in. A red giant, a supernova, an asymptotic giant branch star. Each type of star has its own chemical fingerprint, and those fingerprints are preserved in these tiny grains, no bigger than a few micrometers across. It's hard to overstate how remarkable this is. We're holding pieces of stars that died before the sun was born. We're studying material that's 7, 8, even 9 billion years old. Material that's traveled across the galaxy through unimaginable spans of time and space to end up here, on Earth, in our hands, in our laboratories. It's like receiving messages from the deep past, messages written in atoms and isotopes, telling us about the life cycles of stars, about nucleosynthesis, about the evolution of the galaxy. And all of this from meteorites. From these rocks that fall from the sky. It's easy to walk past a meteorite and not give it a second thought. It looks like a rock. It sits on a shelf or behind glass, static and silent. But when you understand what it contains, it becomes something else entirely. It becomes a time capsule, a library, a teacher. You can let your mind wander with this idea for a bit. Imagine a library, but instead of books, it's filled with meteorites. Each one on a shelf, carefully labeled, and each one contains information, stories, data. If you could read them, if you had the tools and the knowledge, you could learn about the formation of the solar system, about the processes that occur in asteroid cores, about the chemistry of the early sun, about the stars that existed before our sun. It's all there, encoded in the minerals, the isotopes, the crystal structures, and scientists are reading these books, slowly, carefully, page by page. With each new meteorite they study, they add to our understanding, they fill in gaps. They answer old questions and raise new ones. It's patient work, meticulous work, but it's profoundly important because these are the only samples we have of the ancient solar system. We can't visit the solar nebula as it was collapsing, but we can study meteorites. And in doing so, we can reconstruct what happened. We can piece together the story. It's similar to the way archaeologists work. They dig through layers of earth, uncovering pottery shards and tools and bones. And from these fragments, they reconstruct ancient civilizations. They figure out how people lived, what they ate, how they organized their societies. Meteoriticists do the same thing, but on a cosmic scale. They dig through layers of rock, uncovering minerals and crystals and organic molecules. And from these fragments, they reconstruct the early solar system. They figure out how planets formed, what conditions were like, how the raw materials of life were distributed. And just like archaeology, it's not always straightforward. Sometimes the evidence is ambiguous. Sometimes different meteorites tell slightly different stories. Sometimes there are gaps in the record, but over time, with enough data, with enough careful analysis, a picture emerges. Not a complete picture, perhaps. Not a perfect picture, but a picture nonetheless. A story that's grounded in evidence, in observation, and the scientific method. And that story is still being written. New meteorites are found every year. New techniques are developed for analyzing them. New discoveries are made. Just recently, samples were returned from an asteroid called Bennu by NASA's OSIRIS-REx mission. These aren't meteorites, technically, because they were collected directly from the asteroid's surface, rather than falling to Earth, but they're being studied in much the same way. And they're providing new insights into the composition of asteroids, into the delivery of water and organic materials to Earth, into the processes that shape small bodies in the solar system. The Japanese space agency JAXA has also returned samples from asteroids, first from Itokawa and then from Ryugu. Each mission brings back just a few grams of material, sometimes less. But those few grams are incredibly valuable. They're pristine, uncontaminated by Earth's atmosphere or biosphere. They represent the asteroid as it exists in space, not as it appears after falling through our sky and landing on our planet. And what these samples show is that asteroids are more complex than we once thought. They're not just inert chunks of rock. They've been altered by space weathering, by impacts, by the solar wind. Some contain water-bearing minerals. Some contain organic molecules. They're dynamic objects with their own histories. And by studying them, we're learning not just about asteroids, but about the entire solar system, about how it formed, how it evolved, how it continues to change. Let your thoughts drift with this. The idea that small rocks, whether they fall from the sky or are carefully collected by spacecraft, can tell us so much, can open windows into the past, can help us understand our origins. It's one of the beautiful things about science, the way it takes the small and the ordinary and reveals the extraordinary within it. A meteorite is just a rock until you look closer, until you analyze it, until you understand what it represents. And then it becomes a messenger, a teacher, a bridge between past and present, between the known and the unknown. Now think about the future for a moment. What role will meteors play in the years and decades and centuries to come? Will we still study them? Will we still be fascinated by them? Almost certainly. But the way we study them might change. The tools we use, the questions we ask. Already there are proposals to visit more asteroids, to bring back more samples, to study them in greater detail than ever before. Some scientists want to send missions to comets, to collect samples from their nuclei and tails, to understand how these icy bodies form and evolve. Others want to visit the outer solar system, to study the Kuiper Belt objects and the Oort cloud, regions where comets originate. And there are even proposals, still in the early stages, to capture a small asteroid and bring it into orbit around the moon. From there, astronauts could visit it, study it, mine it for resources. This might sound like science fiction, but the technology is almost within reach. We've already sent spacecraft to asteroids. We've already collected samples. The next step is to bring a larger piece back, to make these objects accessible not just to robotic probes, but to human explorers. Why would we do this? Partly for science, to learn more about the solar system, to understand the processes that shape small bodies, but also for practical reasons. Asteroids contain valuable materials. Water, which can be broken down into hydrogen and oxygen for rocket fuel. Metals like iron, nickel, platinum. Rare earth elements. If we ever want to build large structures in space, or send missions to Mars and beyond, we'll need resources. And rather than launching everything from Earth, which is expensive and difficult, it might make more sense to mine asteroids. To use the resources that are already out there, drifting in orbit. This is still a long way off. Decades, maybe longer. But it's not impossible. And meteors, in a sense, have been giving us a preview of what's out there. Every meteorite that falls to Earth is a sample from an asteroid or a comet. A free sample, delivered by gravity and chance. We've been studying these samples for centuries, and now, slowly, we're beginning to think about going out there ourselves, about visiting the sources, about bringing back material in larger quantities. It's an exciting prospect, but you don't need to worry about the details. Not tonight. Just let the idea wash over you. The idea that meteors, these quiet visitors, have been teaching us, preparing us, showing us what the solar system contains, and that someday maybe we'll venture out and see it all for ourselves. For now, though, let's return to something simpler, quieter. Let's think about what it's like to watch a meteor on a clear night. Not in a scientific sense, but in a personal one. Emotional. Even you're lying on your back. The ground is cool beneath you. The sky is vast above you, scattered with stars. You've been watching for a while now. Your eyes have adjusted to the darkness. You can see more stars than you could at first. Faint ones, distant ones. The Milky Way, if you're far enough from city lights, stretches overhead like a pale ribbon, and then it happens. A meteor, quick and silent. It appears near the horizon, arcs upwards slightly, and then fades. But in those 3 seconds, something shifts inside you. A small shift. Subtle, but real. You're reminded of how big the universe is, how small you are in comparison, but not in a frightening way, because you realize that you're part of it, that the same forces that guide that meteor are guiding you, that you're subject to the same laws of physics, that you're made of the same matter. And there's something deeply reassuring about that, about being part of something so much larger than yourself. It's a feeling that's hard to put into words, but many people have felt it. That sense of connection, of belonging, of being held by the universe, even if the universe doesn't know you exist. Even if you're just one tiny consciousness on one tiny planet, orbiting one average star in one ordinary galaxy among billions. You still matter. Your experience still matters. The fact that you can lie here and watch a meteor and feel wonder, that's not nothing, that's everything. Let that feeling rest with you now. Let it be gentle and soft. There's no need to grasp at it. No need to hold it tightly. Just let it be there, like the warmth of the sun on your skin or the sound of rain on a roof. A simple presence, a quiet truth. We're nearing the end of our journey now. But there's no hurry. No need to rush toward the conclusion. We can take our time. We can let the thoughts unfold slowly, naturally, like dawn spreading across the landscape. There's one more thing worth thinking about, one more question that meteors raise, and that's the question of chance, of randomness, of the role that accident and luck play in the universe. Every meteor that falls to Earth is, in a sense, an accident. That particular fragment, on that particular trajectory, arriving at that particular moment, none of it was planned, none of it was intended. It's just the result of gravity and momentum and billions of years of collisions and interactions. The meteoroid wasn't aiming for Earth. It wasn't trying to become a meteor. It was just following its orbit, following the invisible lines of force that curve through space. And one day, that orbit happened to intersect with Earth's path. The same is true for larger impacts. The asteroid that struck the Yucatan 66 million years ago wasn't targeting the dinosaurs. It wasn't trying to cause an extinction. It was just an object in space, moving according to the laws of physics. And Earth happened to be in the way. If the timing had been slightly different, if Earth had been a few minutes ahead or behind in its orbit, the asteroid would have missed entirely. It would have sailed past, unnoticed, and continued on its journey. And the dinosaurs might still be here. And the dinosaurs might still be here. And we almost certainly wouldn't be. This is the nature of the universe. Chaos and order intertwined. The orbits of planets and asteroids are governed by precise mathematical laws. You can predict where they'll be in a year or 1,000 years with incredible accuracy. And yet, over long timescales, the system is chaotic. Small perturbations get amplified. Orbits shift. Close encounters happen, and the outcome is unpredictable. We can't know which meteors will fall next year. We can't know if a large asteroid will strike Earth in the next century or the next millennium. We can watch the sky. We can track near-Earth objects. We can calculate probabilities. But we can't eliminate the possibility entirely. The universe is too complex, too dynamic. There's always an element of chance, and maybe that's okay. Maybe that's even beautiful, in a strange way, because it means the universe isn't deterministic. It's not running on rails towards some fixed endpoint. It's evolving, changing, creating new possibilities with every passing moment. And we're part of that evolution. We're part of that change. When a meteor falls, it's a tiny reminder of this. A small example of the universe's ongoing creativity. This particular fragment, with this particular composition, on this particular trajectory, creating this particular flash of light, it's unique. It's never happened before, and it will never happen again. Not in exactly the same way. The next meteor will be different. The one after that will be different too. Each one is a singular event. A moment in time that arises and then passes, never to return. Your life is like that too, in a way. You're a unique configuration of matter and energy and consciousness. You exist here and now, but not forever. Someday, like a meteor, you'll pass. You'll transform. The atoms that make up your body will disperse and become part of other structures. Other forms. The universe will continue. And in some distant future, those atoms might become part of something entirely new. A tree. A river. Another person. Another world. This isn't meant to be sad. It's just the way things are, the way they've always been. And there's something comforting in it. If you let yourself see it that way, you're not separate from the universe. You're not fighting against it, you're flowing with it. You're part of the same process that creates stars and planets and meteors. The same cycle of birth and death and transformation. And while you're here, while you exist in this form, you get to experience things. You get to lie under the stars and watch meteors. You get to feel wonder. You get to ask questions and seek answers and marvel at the complexity and beauty of it all. That's a gift, a rare and precious gift. And it doesn't last forever, but that's okay. Nothing does, and that's what makes it meaningful. So let your mind rest on that for a moment. The idea that you're here, now, connected to everything, made of stardust, subject to the same laws as meteors and galaxies. Temporary, but real. Fleeting, but significant. And while you're here, you get to witness, to participate, to be part of the story. The universe has been telling this story for nearly 14 billion years. Stars have formed and died. Galaxies have collided and merged. Planets have come and gone. And through it all, matter has been cycling, transforming, creating new forms, new possibilities. You're one of the ways the universe has organized itself. One of the ways it has become aware of itself. When you watch a meteor, you're not just seeing a rock burn up. You're seeing the universe looking at itself. You're seeing matter observing matter. Energy becoming aware of energy. It's a kind of cosmic recursion. A strange loop. And it's happening right here, right now, in this quiet moment as you lie in the dark, listening to these words, thinking about meteors and stars and the vast, silent expanse of space. You don't need to understand it fully. You don't need to have all the answers. It's okay to sit with the mystery, to let it be unknown, to let it be beautiful and strange and beyond your complete comprehension. That's part of what makes it meaningful. If we understood everything, if we had all the answers, there'd be no wonder left, no room for awe, no space for curiosity. But we don't have all the answers. We don't understand everything. And that's wonderful. That's what keeps us looking up. That's what keeps us asking questions. That's what makes science exciting and art beautiful and life worth living. Meteors are just one small part of this. One thread in the vast tapestry. But they're a thread that connects to so many others. To the formation of the solar system. To the evolution of life on Earth. To the chemistry of the cosmos. To the nature of time and change and impermanence. Pull on that thread and you start to unravel the whole story. Or rather, you start to see how interconnected it all is. How nothing exists in isolation. How everything depends on everything else. And that's a beautiful thought to drift away on. The idea of interconnection. Of belonging. Of being part of something vast and ancient and ongoing. You're not alone. You've never been alone. You're woven into the fabric of reality itself. And that fabric is always here, always present, even when you're not aware of it. So let your awareness fade now, if it wants to. Let your thoughts grow softer, quieter, less distinct. Let the images blur, the words fade, the ideas dissolve. You've journeyed through meteors tonight, through fire and time and space and wonder. And now you can rest. You can let it all go. You can simply be above you right now, even if you can't see it. The sky is there. And somewhere in that sky, at this very moment, a meteor might be falling. A tiny fragment of the solar system, burning brightly for a second or two before vanishing forever. No one might see it. No one might know it happened. But it happened anyway. It was real. It was part of the universe's ongoing story. And you're part of that story too. Always have been. Always will be. Even when you sleep. Even when you dream. Even when you wake tomorrow and return to the ordinary rhythms of life, the connection remains. Quiet, constant, unbreakable. The meteors will keep falling. The stars will keep shining. The universe will keep turning. And you can rest in the knowledge that you're held by it all. Supported by it, made possible by it. There's nothing you need to do. Nothing you need to prove. Just be here. Just breathe. Just drift. If you're still awake, you can close your eyes now. Let the darkness be complete. Let your body settle fully into rest. Your muscles are soft. Your breath is slow. Your mind is quiet. And in this quiet, there's a kind of peace, a kind of stillness that feels both profound and simple at the same time. You might dream tonight. You might dream of stars, of meteors streaking across an endless sky, of ancient rocks drifting through space for billions of years before falling to Earth. Or you might dream of something else entirely, something personal, something strange. Whatever comes, let it come. Dreams are their own kind of universe, their own kind of mystery, and they're yours to explore. But if the dreams don't come, that's okay too. If you simply sleep, deep and dreamless, that's perfect. That's exactly what your body and mind need. Rest, restoration, a chance to let go of the day and prepare for tomorrow. Sleep is one of the most fundamental processes in nature. Almost every living thing does it in some form. It's how we heal, how we process, how we integrate experience and make sense of the world. So let sleep take you now, if it hasn't already. Let it carry you gently into the dark, into the quiet, into the soft, dreamless depth where nothing needs to be understood or explained or remembered, where you can simply exist without thought, without worry, without any effort at all. The meteors will still be there when you wake. The universe will still be turning. The stars will still be shining, even in the daylight when you can't see them. And you'll still be connected to all of it, still part of the story, still held by the same laws and forces that guide everything from the smallest particle to the largest galaxy. But for now, rest, sleep. Let everything else fall away. Let the wonder fade into peace. Let the thoughts dissolve into stillness. Let yourself drift like a meteor through space, silent and weightless and free. Thank you for being here tonight, for listening, for journeying through these ideas and images. If you found comfort in this quiet exploration of meteors and the cosmos, you're always welcome to return whenever you need to drift away again. Deep Somna will be here, waiting, ready to guide you gently towards sleep. Just rest here in the stillness. You are part of this story too. A quiet soul on a quiet permit, spinning softly beneath a sky that never stops moving. If you happen to still be awake, here's another gentle reminder to like and subscribe for more videos like this every day. And feel free to watch the next one on the screen if you're still feeling curious. But if you're ready to drift, then may your dreams be long and filled with wonder. But there's no need to think about that now. No need to think about anything at all. Just let go. Just breathe. Just be. And sleep well. Good night.